Good afternoon, ladies and gentlemen. Welcome to my lecture. What I would like to present to you today is stresses in soil mass. Let's get it started. Now, let us consider a rhombic soil element at a depth z as shown in the figure here. There will be normal stresses, also known as total stresses acting in x, y, and z directions as shown in the figure. In many practical applications, it is not necessary to implement a complex three-dimensional stress analysis. The reason for this is that most of geotechnical structures comprising embankments and retaining walls are long in comparisons with their width and height. That's why it is often simplified to two-dimensional stress state where sigma sub V is the vertical total stress and sigma sub H is the horizontal total stress. The vertical total stress results from the weight of the soil mass above the soil element, and it can be obtained using the unit weight of soil. That is to say, sigma sub V is equal to gamma times Z. In order to determine the horizontal stress, the coefficient of earth pressure at rest, K0, is used. The subscript 0 is used to pinpoint the natural undisturbed earth pressure coefficient in soil mass. So K0 is the ratio between sigma sub H and sigma sub V as illustrated here. In engineering practice, for normally consolidated soils, K0 is sometimes described as 1 minus sine phi, where phi is the internal friction angle of soil. More information about the friction angle will be presented under the related topics later on. To understand the concept of effective stress and pore water pressure, let us consider a plane XX passing through points of interparticle contact in a fully saturated soil as shown in the figure here. If a normal stress applied on the horizontal boundary, then the stress in the soil must be equal and opposite to the total stress for balance. The reaction to total stress is provided by the combination of the stresses from the solids, named as effective stress, and from water in the pores, called pore water pressure. The equilibrium equation can be written as sigma is equal to sigma prime plus U. Sigma is the total stress, sigma prime is the effective stress, and U is the pore water pressure. Now, if we rearrange these equations in terms of effective stress, we get the principles of effective stress definition, which is the difference between total stress and pore water pressure. Now the question is, how can we determine the effective stress when the soil mass is not saturated? In other words, when the soil mass is partially saturated. In that case, part of the void space is occupied by water, as shown in the figure, and part by air. The pore water pressure must always be less than the pore air pressure due to surface tension. Unless the degree of saturation is next to unity, the pore air will form continuous channels through the soil and the pore water will be accumulated around the interparticle contacts. In that case, part of any wavy plane through the soil will therefore pass part through water and part through air. Thus, the effective stress equation for partially saturated soil can be written as sigma prime equals sigma minus UA plus chi times UA minus UW. In this equation, UA is the pore air pressure, UW is the pore water pressure, and chi is a factor depending on the degree of saturation and determined experimentally. It primarily depends on the degree of saturation of the soil. For dry soil, chi is equal to 0. For saturated soil, it is unity. What is the importance of effective stress? The effective stress governs the properties of soil involving its strength, as it carries the weight of engineering structures beyond it. Higher effective stress brings about greater strength of soil and thus the stability of soil mass. Does the effective stress drop to 0? If so, what happens? Well, it is possible. When there is a very high increase in the pore water pressure, the effective stress can become almost 0. In that case, the soil loses its strength and behaves more like a liquid. This condition is usually called liquefaction. It is also named as quick condition, quicksand, and or sand boiling, however you like it. Can the effective stress be negative? In other words, be less than 0? No, it cannot be, because soils cannot maintain tension. As a result, the effective stress cannot be less than 0. The effective vertical stress, owing to the self-weight of soil, can be obtained by considering a soil mass with a horizontal surface, as shown in the figure, and with the groundwater table at a depth of Z sub W. Now, the total vertical stress in this case at depth Z, as shown in the figure here, is equal to the weight of all materials per unit area above the point under consideration. That is to say, sigma vertical is equal to gamma times Z sub W. Gamma is the unit weight of soil layer above the groundwater table, and Z sub W is the thickness of that layer as shown in the figure, plus saturated unit weight, which is the unit weight of soil below the groundwater table, times Z minus Z sub W. Z minus Z sub W is the thickness of the soil layer above the point under consideration. The pore water pressure in the field is associated with the groundwater table. also known as the groundwater level, which is measured by means of piezometers as shown in the figure. The soil below groundwater table is usually considered to be saturated, as mentioned before. Now, in order to calculate the pore water pressure, the distance from the point of interest, as shown in the figure, to the groundwater table is measured and used together with the unit weight of water, as presented in the equation here. Therefore, the effective stress is the difference between total stress and the pore water pressure. If the expressions are put in their places in the equation, and if sigma prime, which is the effective stress, is rearranged, we get sigma prime in the form as presented here. If the soil is above the groundwater table, is it considered to be dry? Well, it may not be, because there is always water that would rise above the groundwater level due to capillary forces. We can understand capillary forces in soils by idealizing the continuous void spaces as capillary tubes illustrated in the figure here. Now consider a single idealized very fine tube submerged into water. Water in this case will rise and remain above the line of atmospheric pressure because of the surface tension. Surface tension is the attractive force implemented at the interface or surface between materials in different physical states. At the triple interface, the water surface is pulled up to a meniscus with the surface tension resultant force acting around its perimeter at an angle alpha to the wall of the glass tube. Now, equating vertical forces at the triple interface. Let us see what they are. The component of the surface tension resultant force acting upwards, and the other is the water force in glass tube acting downwards. Let me also show these in the figure. This is the vertical component of TS, and the other is the water force acting downwards in the glass tube. So if this expression is rearranged, we get an equation for pore water pressure as given here. The pore water pressure can also be expressed as unit weight of water times the height of capillary rise. If we rearrange this expression for the height of capillary rise, we get this equation given here, in which Ts is the surface tension force per unit length, alpha is the contact angle, C is the height of capillary rise as mentioned before, and D is the diameter of the tube, which represents the diameter of the void spaces of soil mass. The surface tension of water is 0.073 Newton per meter, and the contact angle of water with a clean glass surface is 0. Since Ts, U, and gamma water are constants, then the height of capillary rise is proportional to 1 over d. For soils, d is supposed to be equivalent to 0.1 times d sub 10, where d sub 10 is the effective size, which can be obtained from the particle size distribution of soil mass. The meaning of this equation is that the smaller the soil voids, the higher the capillary zone. It is low in coarse grained soils such as gravels and sands. It's about 0.1 to 0.2 meter, but it can reach on average of 7 to 8 meter, even more than that, in fine-grained soils such as silty and clayey soils. The question is, will there be any pore water pressure in soil owing to capillary rise? Well, the pore water pressure, because of the capillarity, is negative, as shown in the figure. And it is a function of the size of the soil voids and the water content. At the groundwater level, the pore water pressure is zero, and it decreases. In other words, it becomes negative as you move up the capillary zone. The negative pore water pressure in soil produces suction, and the suction exerts pressure on soil particles, thus making them more stronger and stable. Since the pore water pressure in capillary zone is negative, the effective stress will increase. For example, for the saturated capillary zone, the pore water pressure at the top is Hc times gamma water. It is negative because it represents the pore water pressure in capillary zone. So the effective stress in this case will be sigma plus Hc times gamma water. If partial saturation is produced by capillary action above Hc, the pore water pressure may be figured out through this equation given here, in which S is the degree of saturation in percent, and Hp is the height of capillary rise in partially saturated zone. However, in practice, the soil above the groundwater level may be assumed to be dry for simplicity. The effective stress at any point in soil mass will vary when water is in motion. To understand these, consider a case where downward seepage takes place through a seabed under gravity as shown in the figure. Let us determine the effective stress at point B beneath seabed. To do this, we need initially to calculate total stress and pore water pressure at point B. The total stress is equal to H times gamma sub W plus Z times gamma sub Z. H is the thickness of seawater, and gamma sub W is the unit weight of water. Z is the distance from the seabed to the point B under consideration, and gamma sub Z is the saturated unit weight of soil beneath seabed. The pore pressure is equal to H plus Z minus delta H times unit weight of water. Notice that the pore pressure at point B is reduced in the amount of delta H times unit weight of water due to seepage. If you don't have any information about seepage and had laws, please watch my earlier lectures on my YouTube channel. Now, the effective stress at point B will be the difference between total stress and pore water pressure. In this equation, we can also include I, which is the hydraulic gradient, instead of delta H, since the hydraulic gradient is equal to delta H over Z. In that case, the effective stress at point B will be in the form given here. This time, let us determine the effective stress considering an upward seepage caused by a layer of aquifer under artesian pressure as shown in the figure here. In this case, the total stress at point B is equal to Z times saturated unit weight of soil. And the pore water pressure at point B is equal to Z plus delta H times unit weight of water. Since the saturated silty clay is under artesian pressure, we need to insert standpipe into the aquifer layer to determine the actual height of water in standpipe. And then we calculate the pore water pressure accordingly as we did in here. Effective stress at point B is equal to total stress minus pore water pressure. Notice that in this case, when the seepage is upwards, the effective stress is reduced by delta H times unit weight of water, contrary to downward seepage explained earlier. At this stage, it is needed to know that delta H over Z is the hydraulic gradient. This is also stressed before. If we rearrange effective stress in terms of hydraulic gradient, we get this equation given here. For your information, hydraulic gradient times unit weight of water is known as seepage force. It has been presented that seepage increases or decreases the effective stress at any point in a soil layer. If the rate of seepage and thus the hydraulic gradient is progressively increased, a limiting condition will be attained where effective stress becomes zero. Remember the case where there was upward seepage and the effective stress was determined at point B. If the effective stress equals to zero, then the critical hydraulic gradient is defined, which is the ratio between effective unit weight of soil and the unit weight of water. Critical hydraulic gradient can also be expressed in terms of specific gravity and the void ratio of soil. Critical hydraulic gradient is about unity for most soils. What happens when the critical hydraulic gradient develops? Well, soil loses its strength and the quick conditions, also known as boiling or liquefaction, takes place. This will have a negative impact on the stability of soil mass as well as the engineering structures standing on it. Now, the question is, what would be the typical example of quick condition caused by seepage? Let me give you a striking example. These may be experienced in the soil next to the downstream face of a sheet pile wall as shown in the figure. Figure shows part of the flow net for seepage under a sheet pile wall and the embedded length of sheet pile wall on the downstream side, which is D. A mass of soil next to the piling may become unstable due to quick condition and cannot support the wall anymore. Mold tests have shown that failure probably takes place within a soil mass of about d times d over 2 in section as illustrated in the figure. Failure leads to surface boiling and total failure of the wall. The hydraulic pressure at the base of soil prism, as shown in the figure here, can be obtained using the flow net. If you don't have any information about these or how to do these, refer to my flow net lecture on my YouTube channel. And after that, the uplift force can be figured out as 1 over 2 times HA times unit weight of water times the thickness of soil prism. In this equation, HA is the average value of head loss at the base of the soil prism, and this can be done by inspection as shown here. The submerged weight of the soil prism acting vertically downwards can be worked out as 1 over 2 times effective unit weight of soil prism times d squared. And therefore, the factor of safety can be defined as a ratio between the effective weight of soil prism and the uplift force. A factor of safety around 3 is usually regarded sufficient. If the factor of safety is inadequate, what measures should be taken then? Well, in that case, either the embedded length of sheet pile may be increased or a surcharge load in the form of filter may be placed on the surface. And the filter material should be designed so that it prevents the entry of soil particles blocking the filter material. Now that if the surcharge load is adopted as a measure, then the factor of safety can be defined as a ratio between total weights and the uplift force acting at the base of soil prism. The effective weights are the effective weight of soil prism plus the effective weight of filter material placed on soil prism under consideration. To better understand what we have learned so far, Let us go through some solved examples. The first one is an idealized soil profile and the related geotechnical parameters given in the figure was presented through boreholes at a site investigation and the laboratory test results. You are asked to calculate and plot the variation of vertical total stress, pore water pressure, and effective stress with depth. The first step is to calculate the unit weights of each soil layer. For silty sand, given are the degree of saturation, water content, and specific gravity. Based on these data, we first calculate the void ratio and then the unit weight of soil. Now, following the same procedure for fine sand, and for soft clay, the related unit weights are determined. Thereafter, total stress, pore water pressure, and effective stress for each depth are calculated and tabulated as shown. As a final step, variation of total stress, pore water pressure, and effective stress can be plotted as illustrated in the figure here. Second example is a cut for foundation is to be designed in a stiff saturated clay soil as shown in the figure. Estimate the maximum cut that can be made so that the stability of this clay layer is not lost. Suppose that there is no significant change in the groundwater condition during excavation. In the first step, the vertical total stress at point A is calculated as given here. In the second step, the pore water pressure at point A is worked out. In the third step, the effective stress at point A is determined, which is the difference between total stress and pore water pressure. For the quick condition to take place, effective stress at point A should be 0. So we get this equation. Solving this equation, we obtain that age is 6.83 meter. Therefore, the depth of maximum excavation should be less than that for the stability condition. Now you have a final but a smart example. For irrigation purpose, water from the lake is to be pumped. As a result, the water level in the lake will decrease. So at what level of water in the lake will the quick conditions take place at point A? As a first step, we need to calculate the critical hydraulic gradient, which is the ratio between the effective unit weight of clay soil and the unit weight of water, which gives us a value of 0.76. In the second step, the present hydraulic gradient is needed to be calculated. It is delta H over L. Delta H is the head difference between water levels, the difference between the water level in the piezometer and the water level in the lake. So it is not 0.20. As a final step, we need to determine the water level related to the start of quick conditions. In this case, the critical hydraulic gradient is the ratio between the head difference. This is the difference between water levels after pumping and the thickness of clay layer under aquifer condition or artesian condition. This results in a height of 2.8 meter. Now, considering that the present water level is 4 meter, then the critical conditions would take place when the water level drops to 1.2 meter. Before you say, oh my goodness, not again, let me quiz you on the main points we have learned so far. The first question, the stress carried by soil solid is called what? Now, be careful. Bully for you. Yes, it is effective stress. Well done. Second question. Capillary action results in what comes after these? Yes, you got it. That's it. The answer is negative pore water pressure. Keep going. The effective stress is increased by what? No, you got it wrong. It's not. No, sorry. The answer is downward seepage. In which soils can capillary rise vary from 0.1 meter to 0.2 meter? Which one? Coarse sand. Well done. So the answer is A. The fifth question, for most of natural soils, the critical hydraulic gradient is considered to be around what? Now, you are talking through your head. Come on. The answer is D. It is around 1. So the final question, hydraulic gradient depends on soil permeability. That is to say, the higher the coefficient of permeability, the greater the hydraulic gradient is. True or false? No, you got it wrong. It is false. That's it. Well, this brings me to the end of my lecture. Thank you for your listening. Have a lovely day.